So next speaker is Radu Grigore, and he's going to talk about why your Java compilation task doesn't terminate over the weekend.
Hello. I'll start with just a short announcement. University of Kent is hiring lots of people. With that out of the way, and they like PL. So let's get back to the paper. The main result of the paper is accurately described by the title, I think, and how you prove that it's kind of complicated. So instead of that, I'm just going to tell you a story of how this result appeared. It's going to be a partial story because there's not too much time, and starts in a time long ago when mobile phones took very blurry pictures. And Knut was in the situation, and we knew that push-down automata and context-free grammars define the same languages, and he defined these LR grammars. Kursel showed what the first sentence of the abstract says. It says, the real-time one-state deterministic push-down automata with jumps define the family of deterministic languages. What does that mean? Well, real-time means that you put a restriction on deterministic push-down automata. You ask them to have sort of one transition, one letter that is being processed, which is not the case for normal ones. But on the other hand, you put this restriction, but also enhance them because you add an operation, the jump, which is something that they can do in the stack they couldn't do before. And what he shows is, well, if you give me an arbitrary DPDA, then I can construct one of these real-time DPDAs that recognizes the same language. So he's adding a term to this equation. You can also define deterministic languages like this. Now we'll take a break because I'm going to do this in chronological order. You see there's sort of two strands of research. There's not too much crosstalk between them, but somehow both strands were useful. So now I'm moving to the more practical part. So in 2000, Viroli was looking at more practical languages like C++ and Java and generics. And what he did was he said, okay, let's look at how the type checker works. So he was looking at one particular algorithm for type checking. And he noticed that for certain class tables, by class table I mean this bunch of declarations that says which class inherits from which other class, you will have non-termination. And what he came up with a simple check that can apply on a class table. And if this check comes up and says yes, then that means whatever subtype query you come up with, the straightforward algorithm will terminate and say yes or no. But if you apply this simple check on the class table and it says no, then there exists a subtype query that will make the straightforward algorithm not terminate. And these class tables that allow this kind of situation are called now expansive recursive. And what do I mean by the straightforward type checker? Well, imagine a recursive implementation. We have this function, it's called eSubtype. It returns a Boolean. It receives arguments that are the two types. And it says, well, if the first type looks like a C question mark super T1 and the second one looks like same class C question mark super some other type, then I'll just call myself recursively. And how do you figure out this is what you're supposed to do? Well, you look at the Java language specification and you see that this is what it says. You can describe this kind of rules more formally like this. And that's it. Okay, now let's move to the next one, Kennedy and Pierce. So this is the paper where actually you can find the formal system that I'm using and the problem that I managed to solve stated sort of explicitly. So this was in 2007. The paper is about nominal subtyping. That means that you have the class table where you say which class inherits from what other class. So class named C inherits from class named D. With variance, and variance is what you saw in the previous rule where you, to decide some subtype, you sort of descend inside the angle bracket and check some subtyping there. So first, they they said, okay, we have this, what I call the straightforward algorithm. So you basically define the subtyping relation in terms of an algorithm, which is kind of funny. So you have those rules, you interpret them inductively with that recursive implementation I mentioned, and you say if it terminates and the answer is yes, and the subtyping relation holds. Otherwise it's not. Does it make sense? And well, it kind of makes sense because you have nice properties that you'd expect from a subtyping relation, like transitivity and so on. So that's the first thing that they do. It's a minor point in the paper, but I think it's interesting to be aware of it. Somehow I found it important. The second question they address is, okay, we know that straightforward type checker does not always terminate, but can you find another one that always terminates and does sort of the same thing? So use the straightforward one as a reference implementation, but you want one that always terminates. Can you do that? And they said, no, we cannot do that, because if you do that, you solve the post-correspondence problem. So is the story over? Well, it's not quite over because of this. It says, this is a quote from the article. It says, we conjecture that undecidability critically depends on the combination of three features that are not found together, in particular in Java. So what are these three features? The first one is contravariance, which is what you saw in that rule, where to check subtype, you descend in the angle brackets and swap the direction. The second feature is basically that you need something that does not pass the criterion of Viroli. They have to be not expansive recursive because, they have to be expansive recursive because otherwise even the straightforward algorithm terminates. And the third criterion is this. It says class hierarchies in which a type may have multiple supertypes with the same head constructor. So what does this mean? Well, if you have you have a class table and you fix two classes, C and D, then you can try to find the path from C, going to supertypes all the time, to D. And while you do this, you accumulate some stuff in the type arguments. Now, it's possible that you can do this in multiple ways, and now it's possible that what you accumulate in the argument is sort of different. So if that's the case, then the straightforward algorithm sort of needs to try all possibilities. And this is a feature that is used in the reduction. So the reduction is from post-correspondence problem. You need to look at all sequence, all permutations of something. So to look at multiple possibilities, they use this branching that is possible because of having multiple paths in the class hierarchies, and they're and these kind of paths are not allowed in Java. So basically, what's happening here is they have some mathematical model that kind of approximates what Java does, but it does a little bit extra, and the reduction uses that little bit extra. So the result does not apply to the whole language. Then there's another paper that appeared 2 years later, which asks the question, is there a type checker that always terminates? And they say no, by reduction from the post-correspondence problem. And you might think that you saw this slide before, and that's true. The papers, when viewed from this very high vantage point and in very blurry terms, are very similar. But if you look at the details, they're completely different. So all the math is different because they use a completely different formal model to approximate what you find in the Java language specification. So what they do is something like this. They have a first stage where you go from types with wildcards that you can write in Java to types with existentials and bounds. And then they define subtyping for that and prove that that subtyping is undecidable. But again, the reduction uses some of these subtypes with existentials that you cannot get by the sugaring from the wildcards. So we're now in this situation where we have two undecidability results that kind of hint that it might be undecidable in Java. We also have this, if you read carefully in Kennedy Pierce, there is some conjecture that says that maybe it's decidable if you can't branch in several places. So the situation is a little bit bothersome, and people don't like Java type system maybe for other reasons as well. So there's been work on trying to improve it. I'm going to highlight just two pieces of work in that vein. And usually they say our proposal is better because blah, 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 and it's decidable. And it kind of feels like they would have liked to say, which is not the case for Java, but they can't say that. So one of them is this one, the taming wildcard paper. What they do in this is they say, well, people think of wildcards as being standing for some type that you don't know or you don't want to write down. And they come up with an example where this intuition is sort of not really what happens. So basically, you ask a subtyping query with a wildcard, you apply the straightforward algorithm, it says yes, you have a subtype in relation. And if you look at what the algorithm does, you see that it actually kind of instantiates the question mark some particular type. So then you'd think that, okay, now if you change the subtyping query by plugging in that particular type instead of question mark and asking now if it's a subtype, it should still work, but it doesn't. And they say we can fix it if you go to co-induction. So in terms of this recursive implementation that I mentioned, if you want to check that T1 is a subtype of T2, you have some recursive call, and you say, oh, now you need to show that T1 is a subtype of T2. The straightforward algorithm that I mentioned will just not terminate because we'll do that again and again. The co-inductive one just return true the second time. So in several situations where the inductive one does not terminate, this one will terminate and will say yes or no, and somehow it also corresponds better to the intuition of what wildcard mean. And also then they say if you make this change and if you put some extra restrictions, syntactic restrictions on we can put question mark super, then you get decidability, and that's good. Now the other paper about shapes, it says, you know, instead of classes, we should have two different concepts, shapes and materials. And if you do that, you can tweak the type system a little bit. And guess what's the one advantage if you get if you have that? It's decidable. And also, compared to the other proposal with question mark super, they found that if any code they looked at, they were able to classify these classes in either shape or materials in such a way that the program still type checks. So it's sort of more backward compatible. While the other one with question mark super, there's some things that people might reasonably write that are forbidden. Okay, so now we finished with the left branch and we can get back to the push-down automata that you saw earlier. This happened fairly recently at eCoop, and it was actually reading this paper that I started thinking about this problem. So what they show here is that you can coerce the Java type checker to recognize deterministic languages. And how do they do it? Don't have a point. Anyway, how do they do it? They do it in two steps. In one of them, they show all kinds of tricks, how you can make the Java type checker simulate a real-time jump TPDA, and then they invoke this result from Cursal. They use generics in these tricks that they do, but they don't use variants of the generics. They do use some other kind of variants, this covariance of returns of methods in subtypes and some other stuff. So it looks very complicated. They use many things, but not covariance of generics, and they simulate real-time jump DPDAs. Okay, and finally we get to this one that I'm presenting today. What did I do? I said, well, subtyping is undecidable. So it's basically the same result as in Kennedy and Pierce, Ver and Tiemann. Those who were different because they were using completely different formal models about what Java does. I'm not using a new model. I'm using exactly the one from Kennedy and Pierce, but I put this restriction that I allow myself to only use class tables that are legal in Java. So they're unambiguous in the sense there's sort of only one path in the class inheritance table. So there's no way to do splitting. At any point, the straightforward type checker, there's only one thing it can do, but you still have the question, will it go on forever or not? And even in that case, it's undecidable. The basic outline of the proof is this. If you give me a Turing machine and an input tape, here's a procedure that generates a class table and a subtype query, according to which, and then if you write the straightforward type checker, that will simulate the Turing machine. So if you want to do better than that, then you need to solve the halting problem. So that's the brief version. Okay. And so the main advantage of this is that, well, you restrict what you can generate, and it applies to Java. So you can sort of use it there. So in particular, if you look at that proof, it immediately follows that you can have a slightly stronger result than GLL. You can recognize any context-free language in polynomial time. How do you do it? Well, somebody gives you a grammar. You generate a parser for that. We know how to do polynomial time parsers. You can implement that in a Turing machine. You apply this reduction to get a class table. That's going to be polynomial as well, so you have to check that it's polynomial. It is. And then you use the straightforward type checker. So there is a type checker that will work in polynomial time, and the one in Java basically is the straightforward, what they call the straightforward one. And if you look at Gil and Levy, you see that they propose some application for this. So when you design APIs, you might be able to describe them in a declarative way and use some sort of parser generators for APIs, just like we use sometimes parser generators for normal parsing. But the problem is it's polynomial time, but really slow. Okay, so the proof is obvious, what I told you. Okay. The proof of the second part is obvious, but the reduction is not quite so obvious. It's a bit tricky, and so it's possible to get it wrong. And what can you do about that? When one thing I put this on archive a long time ago, hoping that people will look at it and find mistakes. I don't know if that happened. If it happened, I was not told. So I hope it's okay. The other thing that you can do is, this is basically a procedure, so you can implement it. Of course, it has to work for all Turing machines, but you can feed it one Turing machine and compile it to a class table and see if it works. Now, here I have 2 minutes. I was thinking of showing you this. Maybe I have time to show you? I think I have time in 2 minutes. Let's see. Okay. Oops. This is empty. I'm gonna copy a pre-made Turing machine. So this is some Turing machine that is supposed to recognize palindromes. And then what you can do is you can generate some Java code from it that looks like this. Now, when I compile it, nothing happens, but then if I want to run it, I need to give it some input. Sorry, I keep doing this. So this one, for example, so what you do is you specify the tape here between start and stop. So this is the empty word. So this should be a palindrome, right? So now if I compile it, it compiles because that is a palindrome. But if I change this file and I say, I don't know, A, B, then there should not be a palindrome, and it says, oh, there's a type error. And you can do this with many Turing machines to check that what you expect to happen will happen. Okay, so that's all. Thank you.
Any questions? Andrew.
Very nice talk. I wonder what you would suggest to the Java language designers that they should do about the Java type system.
I was afraid somebody will ask that. So I don't know what should be done. I think this is one piece of information they should take into account. So for example, I heard there is some talk about having reified generics. So if you have reified generics, the problem is then you have this instance of operator, which then you can't guarantee that it will always terminate if it takes into account the type parameters. So you could possibly think of that as being a target for security attacks, just like array out of bounds is a target for security attacks. So it's it could happen. So it's something bad could happen. Now on the other side, you could just say, well, we want to have it. It's okay to have this feature in the type system, and maybe actually we just want to change the type checker so that it handles these kinds of programs much faster, and then you can have parser generators for Fluent APIs. But these are possibilities. So if you want to take decisions about language design, you have to have a lot more experience in working with many people and see how they react to language features than I have. So I don't want to give advice on what to do.
Other questions? We have the next speaker.
There's someone.
Yeah, Phil.
You turn it on. No, it's on. Right. So two things. First of all, I want to say it's not Martin Odevsky and I's fault. When Gilad put things like super into the generics for Java, we said, please don't do that. But he did. But the other thing is, you're selling this as a bug. I'm wondering if it shouldn't be sold as a feature. Right? We saw Stephanie's talk this morning saying sometimes you want to do lots of computation in the type system. So all you need to do is apply Turing's second paper about Turing machines. So after Turing went to work for Alonzo Church, he wrote a paper giving the translation of lambda calculus into a Turing machine and vice versa to prove that they were equivalent. And if you ever go and read that paper, you will see that Turing's phrase was, so this shows that we can abandon Turing machines. Well, he didn't call them Turing machines, but we can abandon them. And this phrase he did use, the more elegant lambda expressions. Right? So right from the beginning, it was understood that functional programming was better, at least by some people. So if you just apply that work to translate lambda expressions into Turing machines, now you've got something where you can write a functional program and execute it in Java's type system. And so anything that Stephanie showed us this morning about you do this in Haskell's type system and anything else that's computable, you could guarantee to do. And you could advertise Java as being even better than Haskell for dependently typed programming. So I want to suggest that you take your wonderful implementation and do an extension of it by composing it with Turing's work. And that might actually turn out to be, for God's sake, practically useful. I know as a theorist you probably wouldn't want to do that, but there we go.
Okay, so I see this mathematical result which is true and can be interpreted both negatively and positively. I personally don't really lean too much on either side. I agree that dependently typed programming is kind of nice sometimes, but I think that the route you're proposing for Java is probably not the right one.
Let's thank the speaker once more.